Another day and another stream. It's been a while since I did the development stream. Did some gaming yesterday, but I don't think I'll be playing any games today. This will probably take all my brain power, since we're getting into some advanced topics. It looks like it, at least. I'm gonna be honest, I practically don't remember anything from last time, so I'm gonna have to reread the 10th exercise. I think it's something I should be able to do maybe in 2 sessions. Maybe. I just glanced through it quickly before the stream. But yeah. This is also gonna serve as a benchmark of sorts on the quality of the stream on the VOD. I'm a bit unsure on how well the quality will translate when it's 1080p, since I'm using another streaming software or a streaming service. The bitrate is much lower for a start. So yeah, I wasn't really that, how should I say it? I was kind of disappointed in the video quality on the gaming stream yesterday when I checked it today. But that might be YouTube compressing the video afterwards. I'm not entirely sure. But enough about that. Let's get right into it. So, great. Exercise 10. NumPy/PyTorch warm-up. You learn stable softmax, log softmax, cross entropy, autograd, and tiny training loop. Minimal files plus test below. Drop them in. I'm not gonna drop them in though. I'm still gonna write it out myself. Even though that's slower, it feels like I'm learning better if I do it myself. So we have one script here. And it's still in Python. And we have another script here. A longer one. And here we have a test file to test the math. So the math is mathing correctly. And another test file. And then we can run it. So why these pieces? stable softmax, log softmax, subtracting the max. Log some exp trick, prevents overflow, underflow. This matters for training stability. Cross entropy. We compute minus log softmax at the target index, then mean over the batch. Exactly what f.cross entropy does. Mean. What's the mean value again? It's not average. It's the centermost value, I think. It's been so long since I've done math like this. It's better to simply ask, I think. What does mean stand for in mathematics?
In math, mean is basically just another word for the average. So if you've got a bunch of numbers, you add them all up and then divide by how many numbers there are. That result is the mean.
Then what is the word for when you have like a sequence of numbers and you select the middlemost one in the sequence?
That's called the median. So if you line up all your numbers in order and then pick the one that's right in the middle, that's the median. If you've got an even number of numbers, you just take the average of the two middle ones, and that's your median.
That always confuses me. So the mean is the average. Okay. Where were we here? Then mean over the batch, exactly what f.cross entropy does. Autograd sanity, finite differences check the PyTorch gradient matches a numeric approximation on a tiny linear model. Training loop shows the minimal pattern forward, loss, zero grad, backward step, and validates that the model actually learns. When this is green, we'll use the tokenizer to build a tiny dataset and hook a mini transformer onto this foundation next. Okay. So, explain to me why I need numpy slash pytorch and what's the purpose in relation to my goals. Short answer, you can write a tokenizer in plain Python, but you can't train a neural net efficiently in plain Python. NumPy and PyTorch gives you the fast vectorized math and automatic differentiation you need to build and train your tiny LLM. Vectorized math. This is gonna be complex, I think. Maybe. I have a friend who does machine learning stuff, and he said it's not that difficult. But I mean, he studied at a very prestigious school for data science and mathematics, so I don't really trust his word. How they fit your goal. NumPy, learn and prototype the math. What it is, fast n-dimensional arrays. N-dimensional is as in like 1-dimensional, 2-dimensional, 3-dimensional, or does n stand for something else here? It's probably simply a placeholder for whatever. Probably. Let's hope so. Plus vectorized operations runs in C under the hood, so it's very fast. Why you need it? To understand / verify core math. Softmax, log softmax, cross entropy, normalization without autograd magic. Auto, I suppose. This has to stand for automatic gradient or something, maybe? I've seen like images of like LLM weights and stuff, and it's almost like a gradient field for the weights. Maybe that's what we're talking about here. Maybe. Where it shows up, you'll send to check your math against PyTorch, write tiny numeric demos, and build intuition for stability tricks. For example, subtract max before exp. I have no idea what this even means. PyTorch. Build and train the model. What it is? Tensors like NumPy plus autograd, automatic. Oh, okay, here's this automatic gradients. I might have simply remembered that from the last time 2.5 weeks ago when I read it, maybe. Plus GPU support, plus layers / optimizers. So we call NumPy a tensor. Okay, and you have automatic gradients on top of that, plus the GPU support. And I don't know what layers are, but optimizers is probably pretty self-explanatory. Why you need it? Training equals compute loss to compute gradients to update millions of parameters. Autograd does the backprop for you. CUDA / optimize kernels do it fast. Wedge shows up on your mini transformer. Embeddings, lookup tables equals big matrices. Okay, attention, batched mix matrix multiplies. Okay. I have no idea. Done with tensor operations. MLP / layer norm / residuals, standard layers from torch.nn. Loss / optimizer, f.cross entropy plus torch.optim.adam. Adam, probably. Or SGD. Training loop forward, loss 0 grad, backward step. I'm a bit confused about. Is here forward? What's forward? Is it forwarding something to something and then doing the math? Getting it back? I don't know. Division of labor in your project. So tokenizer, BP / byte BP. Plain Python is fine for what you've done. It outputs token IDs. So this here, basically. Data pipeline. Turn token IDs into training sequences / batches. Can be Python or PyTorch. Okay. So we need to take the output from the tokenizer and somehow turn it into sequences / batches. Dataset / data loader. I don't know if this is simply two different ways to name them or if there's a deeper meaning here. Then model plus training. PyTorch for everything from embeddings onward. NumPy remains useful for quick checks and small experiments. Okay. So NumPy is simply going to be for learning the math, and after that we're going to use PyTorch for everything, basically, since it contains NumPy already. CPU as a GPU. Your tiny model will train on CPU just fine for learning. If you add a GPU later, PyTorch can use it with minimal code changes. Okay, that's good to know. Okay, here, mental pipeline. So we have the text. When we pass it through the tokenizer, get the IDs, and then we turn them into batches. And that's the, what do we call it? The data pipeline. PyTorch tensors. Like NumPy probably, something similar. Then we pass that on along to the model, which we have in, which is in PyTorch, and then we get tricky with logits, cross entropy loss, and autograd computes gradient, optimizer updates weights, decode samples with tokenizer. Why are we doing the NumPy PyTorch warm-up now? It teaches the exact primitives you'll use in these transformers: stable log softmax, cross entropy, tensor shapes batching, and the training loop pattern. You'll reuse this understanding when we implement attention, embeddings, and end-to-end training script. If this makes sense, we'll keep XXL focused. Implement stable softmax / log softmax / cross entropy in NumPy. Mirror them in PyTorch, confirm they match, then run a tiny training loop to prove the pieces work. I mean, the exercise steps make sense, I suppose. I simply don't understand what softmax, log softmax, and cross entropy refers to in this case. Log is probably something for logarithm or something like that. But cross entropy, I have no idea. I should also... it always says drop them into a sandbox, but I should probably clarify. Remember going forward that I'm not simply copy pasting your code, but writing it myself from scratch. The end result may be similar, but this way makes learning not more efficient, definitely not. Or maybe you could say more efficient, since it makes me, it forces me to actually confront my lacking understanding. The end result may be similar, but this makes learning take a deeper root. End result may be identical, should I say? Otherwise, it might be confused. Makes, or should I say, makes me learn better. Probably better to use a simple language. See if it's saves that to its memory, or if it's simply going to note that down somewhere. Wait, adjust in teaching style. Okay. This is interesting, because I'm fairly sure that I actually already told it this like at the very start, but I might have forgotten it somewhere. Wait, I'll give specs, invariants, and acceptance checks. No dropping code. This is probably more confusing. Not gonna lie. Since now I don't have anything to go on. What should I say? I mean, I'm missing so much information. Rufus is simply... He's simply taking for granted that I know what all of this means, like Hero Max before EXP and all of that. You misunderstand. I'm way out of my depth without the code to copy. Maybe the copy and paste was what confused it for it. Because I am technically copy and pasting it, but not in one fell swoop. Without the code to reference, maybe. This way you just laid out the exercise feels like I've missed. No, I don't know. Half a dozen exercises. I might be making it worse by trying to explain myself. So I guess I could start with at least creating the necessary files. So we have np. Wait, I need to move my keyboard over. np torch basics.py. Okay, so from future import annotations. Let's wait with this before actually checking the latest here. You're right, my last spec only dumps jump too far. Let's course correct. Here's a small self-contained reference pack you can read, retype and run. It course the exact math you will need next. Keep it open while you write your own version from scratch. How to use this without copy pasting. Read a reference block, then close it and retype the same functionality into your own file. This is impossible. I can't simply read all of this and then simply... Then I'm supposed to somehow remember it, like do it like that, and then simply remember all of this. This is entirely new to me. I mean, I don't know what this means. Or that, or that, or that, or that. Well, I know what this is, but I don't know why it's there. So I think might actually be a good idea to kick on some brakes and slow everything down a bit, because this is I mean, all that I can get from this is like, this is a function, and here we have, wait, I've already forgotten what you call them, not attributes. Yes, no, it's not variables. You call them attributes. No. Something similar like that. Anyhow, it's a function, and this is what we return. Here is a comment attached to the function itself, or a not a comment exactly, or yes, a comment, but a comment that you can reference from somewhere else. But what's an NP? NumPy, I suppose. You know what? Let's just try writing this out and see how much information I'm actually missing. So import NumPy as NP, and import torch. No, not simply torch. Import torch.nn dot functional as f. Okay. Why is it red? Wait, am I missing them from... I might be missing the modules. Let's go back to the original exercise 10, since you don't seem to understand my actual issue with it. Let's start by that, and then I can ask it about this. I'm worried if I ask it right now, it might confuse my question with this, and here we only have only NumPy. We don't have torch or anything like that. Okay, understood. Let's revert. Exactly as originally intended. Clear specs. Was ready to run tests. You'll write the code yourself to make the tests pass. Yes. So it still remembers that I'm writing it myself. That's interesting. Okay, exercise 10. NumPy / practice warm up. Create this file. np torch basics. np torch basics apply. Implement these 4 pure functions. Wait. Are you for real? You implement. But how am I supposed to implement them? I actually made it worse. Trying to optimize the learning or the teaching behavior, and I actually made it worse. How am I supposed to implement these if I have no idea what even numpy is, or PyTorch, or whatever? I'm entirely new to this and have no idea what's going on. Let's see what it says to this. I mean, I could just go back and like reference the previous stuff it spat out, but that might set a bad example for the future. And it would be pretty annoying if each exercise just became more and more abstract, requiring me to like research all of the stuff at the side. I won't be using a textbook or a YouTube tutorial or anything like that. That would supplant the whole, or it would negate the whole purpose of me trying to learn to create an AI with an AI assistant. Okay, so you're not missing anything. We jumped ahead. Yeah, exactly. Isn't this like a contradiction? This has to be a contradiction. I am missing something because we jumped ahead. Let's make exercise 10 a gentle ramp, so you know what NumPy, PyTorch are and why they matter. Then you'll implement tiny pieces yourself. I'm gonna go ahead and try this. It won't hurt to try and play along. What they are in one breath. NumPy fast arrays plus math. Think supercharged lists that do whole array operations in one shot. Implemented in C. PyTorch, NumPy like tensors, plus autograd, automatic gradients and neural net layers. It's what we'll use to train your tiny transformer. Okay, install and verify. Okay, so here's the installation step then. Let's see, we have terminal. And your venv active. Ooh, how did you activate the venv? I forgot about that. It's something like venv or something like that. How do I activate the venv in my Python project?
Sure, so to activate your virtual environment, you just need to run a simple command. On Windows, you'll go into your project folder and type something like .venv scripts activate in the terminal. That should switch you into the virtual environment, and you'll see your prompt change a bit to show that it's active.
So it's... Here we have the venv, we have the scripts, and here we have the activate. And we need to run this one. So .venv /scripts /activate and enter. Yeah, so now we're in the virtual environment, and since we're there, we can run pip install numpy and torch. I have no idea where it's actually getting all of these modules from. Seems kind of crazy. I don't know where I'm downloading anything from, but I never thought about it before. Installing MP math, type extensions, somfy, numpy, networks X, markup safe, FSSP, FSSPEC, Firelock, Jinja 2, and Torch. A lot of extensions came with those two. Not extensions, packages it says here. I thought you called them modules though. Do you call something like numpy a module or a package?
Yeah, so something like NumPy is generally called a package. Basically, a package is a collection of modules bundled together. So NumPy itself is a package, and inside it there are multiple modules. But in everyday talk, people often just say the NumPy package, and you're good to go.
Okay. Okay. So after that, still in here, I guess. Python C import numpy. Wait, I'm probably in the way. Probably better to put me up here, since I'm doing so much in the terminal anyways. Oh. And torch. Print numpy dot underscore version underscore and print torch dot. This is a it's simply this is simply a tiny script, you could call it. I could simply write the same here or run the script, but I did it in the terminal directly. So I import the numpy and torch and then print the numpy and its version and torch and its version to check that we actually got them installed. So that is working as it should. You should see version numbers printed. If not, tell me the error. So that is working correctly. Okay. NumPy. Feel the basics. Type these in the REPL. REPL. I've forgotten what that's about. What does REPL stand for?
So REPL stands for Read, Eval, Print Loop. Basically, it's just a way of saying it's an interactive environment where you can type in code, it reads what you wrote, evaluates it, prints the result, and then loops back to do it again. So it's that kind of live interactive prompt you get with Python and similar languages.
But when it says type this in a REPL, where is the REPL? It's not like the IDE, like in the developer environment. I shouldn't write it like code. I should write it somewhere else.
Yeah, exactly. So when someone says type it in a REPL, they mean that interactive prompt, not the code editor. In Python, for example, if you just open a terminal and type Python, it will drop you into a REPL where you can type lines and see results immediately. So it's more like a quick scratch pad for testing out code rather than the full development environment.
Okay, so this is simply for testing. I mean, I could write it in here, or I could simply write it up here and then remove it afterwards. There's literally no difference, I don't think. Simply do import numpy as np, and then say a equals np dot array. So numpy dot array, and with 1, 2, and 3, the type equals np dot float 64, and print a plus 10. I don't need to write out the comments though. A times 2, print a at a. That's, I have no idea what that operation even means, but it's probably times itself somehow, or like raised, maybe raised to itself. I don't know. A dot shape of the array. And if we were to run this now, wait, do I call Python? I think I do. Yeah. So plus 10, then we have 11, 12, and 13. 11, 12, and 13. Expect 246, 246. Since it's times 2 here, 246. And dot product expect 14, 14. What dot product? What's a dot product? It's like an at symbol.
Yeah, absolutely. So a dot product is a kind of operation you do on two vectors. You multiply their corresponding elements, and then you add all those results together to get a single number. In Python, especially if you're using something like NumPy, you could actually use the at symbol as a shorthand for doing a dot product between two arrays. So that's a nice little shortcut once you're working with vectors and arrays.
And how does that mean? Like, how do you multiply them together? Is it like you multiply the first item in the array with all the other items in the second array, and then the second item in the first array with all the items in the other array, or how does it work?
Yeah, good question. So it's actually simpler than that. For the dot product, you just multiply each element in the first array by the corresponding element in the second array. So first element times first element, second element times second element, and so on. Then you add all those products together. So you're just matching them up one by one, multiplying pairs, and then summing everything up to get your final dot product.
Okay, that's fairly simple. Then a shape. 3. This has to mean it's 3 in length. It's a one-dimensional array. If it was like... I'm just going to try something. Okay, and this doesn't work. I thought it's if I could like make the array two-dimensional somehow. Array. Oh, it's I forgot about. I increased the time it takes for the tooltip to appear. Or maybe it doesn't appear at all. Print. Okay. It simply doesn't appear on array. I might as well ask the AI one last time. What does np.array.shape do?
So when you use shape on a NumPy array, it basically tells you the dimensions of that array. For example, if you've got a 2D array, .shape might tell you it has 3 rows and 4 columns. If it's a 1D array, it just tells you the number of elements. So it's just a quick way to see the shape or the size of your data structure.
As I thought. Okay, oh, here we have a 2D arrays. I was too hasty. Oh, so we have 2 brackets. Interesting. X equals np.array and double brackets 1, 2, 3, and then comma and 4, 5, 6. D type np.float 64. D type. I suppose this means like the value type or something. And we'll keep them as floats, maybe. Equals np.max. X-axis 1. Keep dims true. Print m and print x minus m. So we create a two-dimensional array. That's 3 across and 3 in the other direction. What do you call it? 3 rows and 3 columns. And we once again use the D type np float 64. And then we set the m variable to np do we call this a variable? Yeah. To np.max, some kind of function that takes the array and checks the axis equals 1, maybe the first axis, maybe like across, and keep dims equals true. No idea what that references. Okay, so when we print, we expect a 3 and 6. Why would you expect a 6? Three, 6. I mean, that's 3 across makes sense, but why is it 6? Why are there 6 columns? And then you have row-wise subtraction, broadcasting. That axis plus keep dims pattern is the entire trick behind stable softmax / log softmax. What does the axis and keep dims equals true do inside the numpy.max?
Yeah, absolutely. So when you're using something like np.max, the axis parameter just tells NumPy which dimension you want to take the maximum over. For instance, if you've got a 2D array and you say axis 0, it'll take the maximum down each column. If you say axis 1, it'll do it across each row. And keep dims true just means that when you take that maximum, the result will keep the same number of dimensions as the original array. So instead of collapsing that axis entirely, it keeps it around with the size of 1. It can be handy if you want to maintain the array shape for further calculations.
Explain that again, but more in depth.
Absolutely, let's break it down a bit more. So when you use npmax and you give it an axis, what you're really doing is telling NumPy which direction to look in. For example, imagine you have a 2D grid of numbers, like a little table. If you say axis 0, you're asking for the maximum value down each column. If you say axis 1, you're asking for the maximum value across each row. Now, about keep dims true, normally when you take the maximum along an axis, the result is a smaller array, because you've kind of squeezed out one dimension. But if you say keep dims true, NumPy will keep that dimension around with the size of 1, so the overall number of dimensions stays the same. That can be really helpful if you need the result to have the same shape for further calculations.
So that returns a array, like that row instead of the value on the row, that max value.
Exactly, you've got it. So when you use keep dims true, instead of just giving you a single number or a smaller array, it returns an array that still has the same number of dimensions. That means you end up with something like a row or a column that still has that dimension in place, just with the maximum values filled in. So it's handy if you need to keep that shape consistent for whatever you're doing next.
But it doesn't keep the values that are outside, like the axis. I mean, if I have axis 1, then it only has the... Oh wait, then it reads... I'm still confused.
Yeah, no worries at all. It's a bit of a tricky concept the first time round. So let's slow it down a bit. If you pick axis 1, you're basically saying, I want the maximum along each row. So what you end up with is one maximum value per row. Now, if you didn't use keep dims, you just get a one-dimensional array of those maximum values. But if you do use keep dims true, you still get one maximum per row, but it keeps that extra dimension so that the result still looks kind of like a 2D array with one column. It doesn't keep the other values from the original array, it just makes sure the shape matches. In other words, it's not going to keep all the maximum values, it's just going to keep the shape of the array so that it still has the same number of dimensions. Hopefully that clears it up a little bit.
And why, when you have a two-dimensional NumPy array, if you have like 3 values in the columns and then 3 values in the rows, if you print that two-dimensional array, why would you expect 3 columns and then 6 rows? Or why would you expect a 6 in the print?
I see where you're coming from. So it really just depends on how you arrange the data. If you have a 2D array and you print it out, the first dimension is the number of rows, and the second is the number of columns. So if you see 6 rows and 3 columns, that just means you have 6 lists of 3 elements each. It's all about the way the data is shaped. So if you're seeing 6 rows and 3 columns, that's just the shape of your array as it's currently laid out. It's really just a matter of how many elements you have in each dimension.
Wait, I might actually be stupid. Now that I'm thinking about it. So is this one row? No, this has to be one column. This keeps tripping me up for some reason. Columns versus rows. Yeah, rows are horizontal and columns are vertical. I don't know why that's tripping me up all the time. But then this should be one row with 3 columns, and this should be the next row with 3 columns. So I don't understand why you get a 6 here, since this should be the number of columns. Or wait. Oh wait, no. I might have made a huge mistake. I was thinking about the shape of the array, not whatever this is. Let's try and printing the x.shape. And now we get 2 rows and 3 columns. Right? Or is it... The question is... I suppose it doesn't matter which one is rows and which ones are columns, as long as you stay consistent. I don't think so, at least. But I might be wrong. I never thought about this before. Or if I have, it's been so long. if I print the shape of a two-dimensional array, the first number, is that the number of columns or the number of rows?
So when you print the shape of a 2D array, the first number is actually the number of rows, and the second number is the number of columns. So if you see a shape like 6, 3, that means you have 6 rows and 3 columns. It's always rows first, then columns.
And is that like a standardized thing? It's always rows first and then columns.
Yeah, exactly. It's a standard convention in NumPy and in a lot of other programming contexts as well. You always list the number of rows first and then the number of columns. So once you get used to it, you'll just always know that shape means rows first, columns second. Keeps things nice and consistent.
And that makes so much sense then with the print m expect 3 and 6. Since if it's this is a row and this is a row, then 3 is the max on one of the rows and 6 is the max on another row. So we'd get 3 and 6 on those 2 rows. Oh, keep dims, keep dimensions probably. What happens if I remove this one? Run it. Ooh. Wait, did I... no? X minus m... Operands could not broadcast together with shapes. And this is an issue with... oh, since we're doing math down here, we need to keep the dimensions somehow to make the minus actually work. And wait, so we're deleting 3 from this row here and 6 from this row. So I suppose M in this case would look like 3, 3, 3 and 6, 6, 6. If you could like write out the dimensions. Maybe. Let's move on. That axis block plus keep dims pattern is the entire trick behind stable softmax / log softmax. I'm just gonna ask what that's about. What do you mean by softmax / log minus softmax?
So that's a bit of a different concept. When we talk about softmax, we're usually talking about a function that turns a set of values into a probability distribution. It takes your numbers, exponentiates them, and then normalizes them so they all add up to 1. It's often used in machine learning to represent probabilities. Now, when you say log softmax, that's just taking the logarithm of those softmax probabilities, which is useful for certain types of calculations where working in the log space is more numerically stable or easier. So it's kind of a standard way to handle probabilities in log form. In short, softmax is for turning numbers into probabilities, and log softmax is just the log of those probabilities.
And what is a log? Is that like a mathematical function?
It sure is. So when we talk about a log, we mean the logarithm, which is a mathematical function that basically tells you what power you need to raise a certain base to in order to get a given number. So for example, the log base 10 of 100 is 2, because 10 to the power of 2 is 100. In programming and a lot of math contexts, when you just say log, it usually means the natural logarithm, which has a base of e, that special mathematical constant. But you can have logarithms of different bases too. So it's definitely a core math function that pops up a lot.
I've completely forgotten about all of that kind of math. But we'll try our best to see how far we get. So next step then, implement 4 numpy functions. You write them. Create np torch basics.py with these signatures. Follow the recipes exactly. Okay. These signatures. I don't know what they mean by signatures. np log sum exp ax is -1, keep teams false. Recipe. Oh, I suppose I should simply do it like this and then create a function called np log sum exp x axis equals -1 and keep dims equals false, probably. And wait, I do like this, right? I think. And then x convert x to float 64. I have no idea what x is. Is x supposed to be a variable that or parameter that I've set the value as? This is valueless, unknown. But since we're going to convert it to float 64, then it should be an array, right? I don't think we just need to like do it like this. Right. This can't be it. Because then if we have m equals max x along axis, keep dims equals true. Along axis, I suppose they mean like axis like this. When we have to do np.max. No, we need to do x.max. No, wait. No, np.max. NumPy. But it complains for some reason. Overload 2 is the closest match. a long axis. I mean, I could simply do it like that, right? Or is he complaining because X isn't a array? It's an unknown. What happens if I do np.array and then like this? I don't know, should I do the type as well? No, probably not. I'm simply assigning it the value here of np.float. I'm not converting it at all, am I? This is very much exposing my lack of knowledge. I don't know if it said it would be like a, what did it say? It's a gentle ramp. This feels anything but gentle. I'm gonna take a short break here. I'll be back in a few minutes. I just need to clear my head a bit and get some fresh air into my room. So I'll be back soon. Alright, I'm back. I'm back. I'd say that this isn't working. I have no idea what I'm doing. I mean, I can't even convert whatever x is supposed to be. Log some x. Well, I can see it here. Now that I'm actually looking for it. So it is an array of 2 rows with 2 columns. But I feel like I'm missing like some sort of math component. Like something crucial. I feel like I'm missing some sort of crucial math knowledge. Like, what's a log? What about softmax? How does this tie together? Now I already asked AI what log stood for, but that conversation isn't taken into consideration here. Okay. Log softmax, and cross entropy. Hopefully it can explain it in a way that's understandable as well. I did study math, like pretty advanced math, but it's been so long since then. It's like, I feel like even if it was simply a year or something, since after I studied it, I would still not remember anything. 1 year is definitely enough when it comes to math for me to forget everything. Okay, so you're not missing secret math, just a few core ideas. Okay, sure. Here's the minimum you need. With tiny numbers you can sanity check. What is log? Natural logarithm. We use natural log base e. In code it's math.log or mp.log. Okay, that's good to know. It's the inverse of exp. That's also good to know. I didn't know this. So if we try to get the logarithm of the inverse of the logarithm, then we get the value itself. Makes sense. And same goes the other way around. As long as x is greater than 0. Okay, some curve shenanigans or whatever, maybe. Key identities. Log a times b equals log a plus log b. Okay, turns multiplication into addition. And log divided by b equals log a minus b. Turns division into subtraction. Why machine learning loves logs. Probabilities are tiny, for example 1 e minus 9, so like 0.000000001, something like that, maybe. Logs keep them numerically sane. Losses become sums of logs instead of products of probabilities. Much easier to optimize. Softmax turn scores into probabilities. You start with any real scores, logits. And what's a score? C equals C1, C2, to C, C, ZC, whatever you say. Softmax makes them a probability vector. So, I mean, this is a lot here. Outputs are all in 0.1 and sum to 1. EXP magnifies differences. If two logits differ by delta, I don't know. I think that's delta, but I'm not sure actually. It's some sort of the probability ratio is e raised to delta. I don't know how it can call this anything but secret math. You're not missing secret math. This is the secret math. This is legit the stuff that I had no idea about. And it's just taking it for granted that I understand all of this. I think. Or can I move on without actually understanding this? So plus one more logit increases odds by E equals okay. Two variants. Argmax preserved. The largest logit gets the highest probability. Shift invariance. Adding the same constant to all logits doesn't change softmax. We exploit this for stability. So concrete example, logits Z equals 2, 1, 3. I don't know why. Is this like array values, or I have no idea. And then we compute them for some reason. exp of 2. I'm not sure what the exp stands for. It's some sort of mathematical function. The inverse of log, but what do you call it? You can't call it experience. What do you call the inverse math function of log?
So the inverse function of a log is called the exponential function. Basically, if you take a logarithm to get a number, the exponential function undoes that by raising the base back to that number. So they're just mathematical inverses of each other. If you take the log of a number and then apply the exponential function, you get back to where you started.
That makes so much sense. Exponential, of course. So exponential of 1 and exponential of minus 3, sum, okay. Probabilities. So P0 is the exponential of the value of the logit divided by the sum, and the same goes for P1 and P2. But I have no idea why you do this. Then log softmax, just the logarithm of softmax. So okay. There's a numerically stable form you'll implement. I'm just gonna ask it, do I need to understand this math to be able to move forward with the exercises? Because this is practically all new to me. Duplicate. Let's see what it says. Seems shocked that I can't follow this math. But I mean, this is advanced math in my book. I might simply be stupid, but no, this is advanced stuff. Adjusting exercise plan, okay. So, okay, short answer, you don't need deep math to move on. You just need a few rules of thumb and to follow some recipes. We'll treat the math bits as APIs with properties for now. The tiny bit you must know, log, inverse of exponential, or logarithm, inverse of exponential. Let us work with tiny probabilities safely. And that's because we can somehow store the very tiny values as logarithms instead of like really tiny float values, perhaps. That might be why they're safe. Because if I'm not entirely mistaken, then floating point values can have some issues when they get too small or too large, I think. Don't quote me on that though. And effects. Log A times B equals log A plus B. Plus log A plus log B. And the division is the same with the log A minus log B instead. Softmax turns any list of scores into probabilities that sum to 1. Okay. Scores. The biggest score gets the biggest probability. Adding the same number to all scores doesn't change the result. Log softmax, the logarithm of those probabilities. Computed stably as logits minus log sum exponential. Is it like the logarithm of the sum of the exponentials? I don't know. Cross entropy. How wrong? Negative log probability of the correct class, lower is better. That's it. No calculus, no proofs. What you actually do in exercise 10, implement 4 numpy functions by following these exact recipes. Axis is always the last dimension in our tests. I'm not totally sure what it means by this. So, okay, here we go again. And another function, and another function. Another function. What about PyTorch? For now, think of PyTorch as a reference we compare against. Your NumPy functions should match torch.softmax, torch.logsoftmax, and torch.nn.functional.crossentropy to tight tolerances. You don't need to understand AutoGrad yet. Just use PyTorch as the oracle that checks your answers. Minimal mental checklist. Pin this. Use flow64 in NumPy to avoid tiny tolerance failures. Always do the max shift inside log sum exp. Log softmax equals logit. There's still so much that I don't know. Okay. Let's see here. So I'm just gonna delete this since this is probably trash. And let's delete this as well, simply to keep it pretty clean. And softmax turns in a list of scores. So what is a score? I was thinking it got the memo and like dumbed it down a lot, but it seems it's still throwing around terms that I'm not familiar with. So a score is a model's raw unnormalized number for each option. What's going on here? It's turning red for some reason. The one's raw unnormalized number for each option before you turn anything into probabilities. Names you'll hear: logits, softmax classifiers. This is simply I'm lost. I'm honestly lost. I mean, I get like 70% maybe, but it's like the last 30% that completely negates any sort of progress that I might make otherwise. I mean, negative log probability of the correct class. What does that even mean? Class of what? Class of... Yeah, class of what? When did classes come into all of this? Let's see. You're not alone. Let's... let's anchor you with a tiny linear path. Follow these 5 micro steps exactly. You'll write the code. I'll give recipes and checks. And Ballad already did this. Okay. Open a Scratch file or the REPL. I'm gonna do a Scratch file. So one vector math. Create an array. First we need to import numpy with as np, and then we need to create an array. So I don't know. A equals np.array, and then 1, 2, and 3, and d type equals float 64. No. np.float64. This is an array then. Wait, isn't this the exact exercise we did last? Okay, I'm just gonna do it again. I need to understand all this. So wait, a plus 10? Okay, or plus equals a plus 10 maybe. Wait, what happens if I print this now? Can I do it like that? The values are correct, so I could simply print it like that. Let's just do the print as well. So a times 2 and print a what did you call this one? Dot product dot itself. So a at a expect 14. And what was this again? It was you take all of the... Wait, this should be... Wait a second. Oh, it's times itself, correct, yeah. So 1 times 1 is 1, 2 times 2 is 4. So it's 5, and then this is 9, so it's 14. And then this one is also doubling it, so this is correct. Then we move on to the 2D axis keep dims. So we make X instead. And we create an np dot array and do double brackets. And make it 1, 2, 3. 4, 5, 6. And wait, no, we need also a comma. And then the type np.float64. And row max with axis 1. So we can call that m for max, np.max x. So arrays like x and axis equals 1, and I keep dims equals true to keep the dimensions, to keep doing the math. And then if we print m, we should get 3 and 6, yes. And subtract that x and print that's from x. So we print x minus m. You should see each row shifted so its max is 0. Since we remove the max from each row. Okay. the max of that row we remove. If those behave, you got the right mental model to implement exercises. Okay. Step 2. Implement np log sum exp. Okay. So we define np log sum exp x axis int equals -1. Keep dims as a bool, default to false. This makes so much sense. We default to -1 and we default to false otherwise. And we return nothing. Okay. Recipe 1. Cast x to float 64. But how do you cast it? I mean, we could create an array, but not once did it explain how you convert it. It's never explained how to convert it to np.float 64. Only how to create a new array with that type value, I suppose. At least I don't think so. I can't remember it being explained. Great question. Cast to float 64 just means make sure you're operating on a numpy array whose d-type is np.float64. 64-bit floats. Here are the practical ways to do it and when to use each. Okay, the one-liner I recommend inside your functions. Works for any input, list, tuple, numpy array, and avoids copies when possible. Okay. So if x is already a float 64, numpy array, no copy. If x is a list float 32, int array, it returns a float 64 array copy. If you already know x is a numpy array, convert dtype with minimal copying. So x equals x.asType, np float 64, copy false. If it's already float 64, returns a view no copy. If not, returns a new float 64 array. Alternative usually not needed here. np.array x. So you can simply set it to an array of itself like this and then copy false. Similar to asArray, but historically more eager to copy. asArray is the conventional choice for ensure array of this d-type. Why should you do this before any math? If x isn't int and you compute... Wait, if x is int and you compute m equals x max and x minus m, that subtraction of is integer math. Bad for softmax. You lose position or get incorrect results before you even call exponential. Using float64 gives you more headroom against overflow, underflow in exponential logarithm, etc. Quick variance to check in your Rappler. After your cast, this should be true. With as array, this often holds when input is already float64. Okay, that's it for the one I recommend. So this is the gold standard, in other words. So x equals np.asArray x dtype np.float 64. Great. Let's see the next step. Here we are. M equals np.max of x. I don't know what it says along axis. Along isn't somewhere like I can't use along axis like this. I need to use axis. Wait, I might need to do axis. Maybe. As this is an integer here. If this is a parameter. Parameter, nice. And this shape like parameter axis. This might work. Because I can't simply write axis, can I? Maybe I can. Anyways, keep dims equals... No, we can simply do... No, we can't. We can't simply pass along the bool. We need to keep dims and keep dims. We need to do it like that, so we also need to do it like this as well then. Probably. And then we call the shift x minus m. Oh, we used a little x. Let's continue with the tiny x. And sum exp equals sum. Or should I do np.sum? Sum and np.sum. What does it say? This is definitely more specific. It wants array. No, let's do a simple sum. Let's see if it complains. exp shift. Wait, here we should be numpy.exponential probably. And it returns a float probably. Oh, so it said, I think. And along the axis, keep dim. Keep dims. That's true. So now it complains. Should I do NP? No, it doesn't complain any longer, so this is probably the correct. And maybe even axis like that. And then we have y equals m plus log of, wait, np.log sum exp. Okay, so if not keep dims, squeeze the reduced axis. I'm not entirely sure what that refers to. I mean, it says if not keep dim, so it's... I suppose I should literally type if not keep dims. So if that parameter is false, then I should do something. The question is what? Squeeze the reduced axis. I should probably ask it. What does this mean and refer to? Squeeze the reduced axis equals remove the size one dimension that was created by a reduction. Context. When you reduce over an axis, for example max, sum or your log sum exp, you can keep that axis as length minus 1 with keep dims equals true, or drop it entirely with keep dims equals false. Input shape and C, reduce over one axis, the C axis. Keep this equals true, result shape. And the reduce axis is still there, but size 1. Keep dims false, result shape, and the reduce axis is removed. Squeezing means converting n1 to n by removing the length minus 1 axis. Why keep it then squeeze later? While computing log softmax, it's convenient to keep dims dimensions, so broadcasting is obvious. What is broadcasting? What is this? Feels like I need to question every term. Broadcasting equals automatic size matching for element-wise operations. The idea, when you do element-wise math, plus minus multiplication division on different shapes, different arrays probably, numpy/pytorch will virtually stretch any axis of size 1 or missing, so the shapes line up without copying data. The 3 rules: right align shapes, compare from the last axis backward. For each axis pair, it's okay if they're equal or one is 1. One can expand. Result shape equals the max along each axis after expansion. If an axis pair is neither equal nor 1, that results in an error. Quick shape examples. So we have 5 and 7. I guess 5 rows and 7 columns minus 5 rows and 1 column. Okay, the result is 5 rows and 7 columns. The 1 expands to 7. What? Uh, 5 rows, 7 columns minus 7 rows, 7 columns. How do I know what this is from this? This has to be rows in this scenario, right? Missing lead axis acts like 1, while this results in error compared to last dimension 7 versus 5. Okay, I have no idea what they mean by this. Row-wise operation, for example. So LC log sum exp logits. What is a logit? It feels like the more I'm questioning it, the further away I get from making progress. Okay, and now we're back to the math. A logit is a model's raw score before you turn it into a probability. In binary classification, one logit C probability of class 1 is... It is... Okay, let me ask it verbally. What's the difference between a logit and a score in LLMs or neural networks?
Yeah, so in the context of neural networks or language models, a logit is basically the raw score that comes out of the model before you turn it into a probability. So it's just a number that the model spits out for each possible class or token. When you apply something like a softmax to those logits, they turn into probabilities. Now, sometimes people say score just to mean that raw output as well. So in a lot of cases, logit and score are used kind of interchangeably. They're both just talking about the number before you transform it into a probability. So it's really just a naming thing. A logit is that raw output, and sometimes people just call it a score.
And you turn that into a probability.
Exactly, that's the idea. So you take those real logits or scores, and you run them through something like a softmax function. Once you do that, they all get turned into probabilities that sum up to 1. And that's how your model decides how likely each possible outcome is. So yeah, that's the whole flow. Logit to probability, and then you've got something you can interpret as a chance or a likelihood.
And all the probabilities, are they like tied to weights or something? Like the over a gradient map, or how does this like where does the like max 1 come in?
Yeah, that's a great question. So the idea is that when you apply something like a softmax, we're turning all those raw scores into a set of probabilities that sum to 1. That means you're normalizing them so that they form a probability distribution. Now, those probabilities do come from the weights and the structure of the neural network. All the layers and weights in your model are working together to produce those logits, and then you transform them into probabilities. So in that sense, yeah, the probabilities are tied to the weights of the network, and all the gradients and training steps adjust those weights so that the probabilities get closer to what you want. And the reason they sum to 1 is just because that's what a probability distribution does. It makes sure all your possible outcomes add up to a total certainty of 1.
And then you'd usually then pick the most probable answer.
Yeah, exactly. Once you've got those probabilities, you typically just pick the one with the highest probability as your final prediction or answer. So the whole idea is to turn those raw model outputs into a nice interpretable probability distribution. And then you just go with the most likely option. It's a pretty neat process.
And where does temperature come into this? Is it to modify the probabilities or the weights or?
Yeah, exactly. So temperature is basically a way to adjust those probabilities and control how confident or spread out they are. If you use a high temperature, the probabilities get more even and the model becomes more exploratory, giving less emphasis to the top choice. If you use a low temperature, the probabilities become more peaked around the most likely option, making the model more confident and deterministic. So it's just a neat way to tweak how the model behaves when it picks a result.
And what does it mean to squeeze a reduced axis in a log sum exponential function in a NumPy?
So when we talk about squeezing a reduced axis in something like a log sum x function, we're basically saying that after you do the reduction, you remove the axis so that the result has fewer dimensions. In other words, if you had a 2D array and you summed over one axis, squeezing just gets rid of that dimension, so the output is simpler. So it's just a way of saying once you've done the math and reduce things along a certain axis, you drop that axis to keep your array nice and tidy. It just makes the output shape a bit more convenient.
And you don't do that before because you need all the axes when you do math operations?
Yeah, exactly. You've got it. You keep all those axes around while you're doing the math because you need the full shape to do the operations properly. Then once you've done that reduction, like summing or taking a log sum x over an axis, then you can squeeze it out at the end to simplify the result. It's kind of like doing all the heavy lifting with the full shape and then cleaning things up afterward.
But how can it keep the shape even though it doesn't keep any values? Like before you do the squeezing. How does that work?
Yeah, it can feel a little bit like a magic trick at first. Basically, before you do the squeezing, the shape is still there because the array is technically holding a dimension of size 1 along that axis. Even though there's only one slot there and no extra meaningful values, the dimension still exists. It's like a placeholder dimension. Once you squeeze it, you're just removing that placeholder dimension. So up until that point, the array is kind of keeping the shape information around so that all your operations line up. And then at the end, you tidy it up by squeezing it away.
So if you do a numpy.max of an array and you don't keep dimensions, what happens then?
Yeah, so if you do something like a numpy max and you don't keep the dimensions, what happens is that the axis you reduced just disappears from the shape entirely. In other words, the resulting array is going to have one fewer dimension. So if you start with a 2D array, when you took the max over one axis, you end up with a 1D array. If you start with a 3D array and reduced over one axis, you get 2D array, and so on. It just means the shape shrinks because that axis is no longer needed.
I feel extremely stupid. Like, I feel like a complete moron. like 1 second I think I'm understanding everything, and then the next second I'm like, I don't know shit, man. I don't know shit. Because before we did the MP max stuff, but then we kept the dimensions to be able to do math on them, to do the shift here. But here it says keep Jim's bool false as a default. So then we wouldn't keep dimensions. But wouldn't that mean that we can't do the math? Since we have a array here. It just doesn't like come together in my head. And then we have some exponential here, where we take the exponential of shift, so this result of this, and I don't know what the axis even does in this case. I suppose this spit out an array. And then we keep the dimensions of this one. And we have the old max whatever, and we add that together with the sum exponential, or the logarithm of the sum exponential, and call that y. This is what we return later, like down here. Why is it complaining about? Is it because I don't have any? Okay, it's because this is empty. But I'm honestly like, I'm honestly stuck on on this squeezing reduced axis stuff. I think understanding this math is gonna take more than one session. And even then, even if I work on this for like, maybe I've worked on this for over 2 hours now, but even if I work like 6 hours, I probably get a very, very shallow understanding at most. But yeah, I'm gonna leave it here, I think. I'm also not gonna finish this one here because I'm still confused. So I should be able to remember tomorrow where I am. And hopefully move on from here. Maybe some sleep will clear my head somewhat, or make some pieces fit together. It isn't the worst idea. But yeah, I think this is it for now. This is definitely the most complex part I've done so far. Definitely. I thought the byte pair encoding was difficult, but that was, well, that was basic programming and logic, and this is math, and math is a completely other beast. So, yeah, I'll end it here for today. I'll take a look at the VOD tomorrow as well. Let's check the quality. See how blurry it looks. Yeah, thank you so much for watching. Smash those buttons and cheers.